So everything you just saw runs solely on human power. That's the power of a cordless drill, or a motor that's small enough to fit in the palm of your hand. This is what Cameron and I do. The whole idea is to be able to do much more with much less, thereby making the impossible possible. These are all problems that involve highly constrained resources. The human engine can only produce a very small amount of power. But these problems are exciting because they force us to think differently. They force us to come up with creative and very unique solutions. It's these types of projects that get me excited about the infinite possibility of this world. So Cameron and I got our start in 2006 working on the human-powered Ornithopter project. The goal here was to achieve an ancient aeronautical dream, to sustain flight like a bird using only human strength. So no propellers, no engines, simply flapping our wings. This is a dream that's been around for hundreds, if not thousands of years. But more recently, this dream has actually been called physically impossible. And the argument goes like this. This is what we call the Great Flight Diagram. If we take everything that flies, insects, birds, bats, we can plot them all on the same curve if we plot mass versus flight velocity. The problem is, as we get bigger, we're flying faster, and as we fly faster, it requires much more power. It requires, as we go up this curve, the power required is going up much faster than the power available from a metabolic engine. And at some point, there's a limit. At some point, it's impossible to fly using only muscle power. At some point, we reach a limit. It's physically impossible to fly using muscle power. That limit's around 10 kilograms. And as you can see, the biggest bird is only about 10 kilograms. They don't come any bigger than that. So how are we going to fly? How is a human going to fly? Evidently, we're much heavier than 10 kilograms. The point is, or what you need to do is effectively get off the curve. For its weight, a human-powered aircraft flies much, much slower, requiring much less power and making this impossibility possible. The cool thing is that it's not about some new age technology. This is just about thinking differently.
So the first person to think differently and get off of this curve was aviation innovator Paul MacCready. He had the insight to build an aircraft that was both incredibly light but also incredibly large and therefore very slow and sufficiently low powered for its human engine. He crossed the English Channel with this aircraft in 1979 and formed the archetype for all future human-powered aircraft. So this tough human-powered aircraft problem had been tackled, but we had to bring something else to the table. We had been doing our studies during our undergrad and graduate work in a lab with 30 years of experience in flapping wing flight. And it's interesting, this problem, because normal aircraft produce lift by just an upwards force on the wings, and then they have jets or propellers to pull them forward through the air. But we have only wings. So flapping wing aircraft need to produce not only an upwards force, but twist to provide the forward force. We saw that it was possible to bring together the human-powered aircraft and the flapping wing aircraft side. And with the right mindset, you've solved half of the problem. When we built the Snowbird human-powered Ornithopter, it was absolutely massive. It had a wingspan of about 32 meters, but weighed only 43 kilograms. And it was a lot more like a model or a toy aircraft than a regular aircraft. It was made from very lightweight, very thin carbon fiber tubes, from foam and very lightweight balsa wood, and also from plastic film. So this was way different than a normal airplane that you see flying through the sky. At the cockpit of this aircraft, in the fuselage, the pilot is driving the wings by doing a leg press. And this allowed us to find an elegant solution to the design. We designed the wing such that when the pilot does this leg press motion, it pulls down, and the wing naturally twists to provide our forward force. We do this by tailoring the interaction of the aerodynamic forces and the structural deformation to get exactly the right movement, very similar to how birds flap their wings. Now, even though that design solution is elegant, operating this airplane is a lot less elegant and very inconvenient. Every morning, we have to assemble it on about 3-meter high ladders, and we have to lift the wings into position with a farm tractor. And because the wind would pick up and carry the airplane away like a kite, we have to get to the runway every morning before the wind, which is usually before sunrise. So in August of 2010, we achieved our project goal and sustained flight with the Snowbird human-powered ornithopter. This was a world first and an incredibly inspiring accomplishment for young people everywhere, as well as the realization of an ancient aeronautical dream. For us, the biggest takeaway from this project was that we had turned work into fun. We had combined all of our interests, including aerospace engineering, aesthetics, athletics, and efficient design. And we had really been able to find something that combined all of our passions and really created a situation in which we could excel. So, looking for our next challenge and creative outlet, we found the human-powered helicopter competition. In 1980, the American Helicopter Society had created the Sikorsky Prize, calling for a human-powered helicopter to fly for 60 seconds and at one point reach an altitude of 3 meters. In 30 years of trying, nobody had come close, but they had this concept of why it should be possible. They had a simple thought experiment that if you tied together 4 of these airplanes, the Albatross that I showed you earlier, you should be able to sustain the requirements of their prize. But that wasn't the only way to do it. It was a very open-ended challenge with no constraints on the design, which means that this is a really great place for us to apply our skills. So they thought it would be possible, but again, in 30 years of trying, it hadn't been done. And a lot of people were starting to say it was impossible. 3 teams during this time had even lifted off the ground, and then for only inches or centimeters in height and seconds in duration. Now, there's a lot to be learned from these teams and what they accomplished, but a serious departure is definitely required. The simple analysis shows that a successful human-powered helicopter has to be absolutely enormous. And despite that, these people had just gone, found the most convenient gym, and said, this is how big we're going to build our helicopter, without really saying this is what the math requires. So we saw that this was a right problem for some out-of-the-box thinking. We designed to build Atlas exactly as big as the math said was necessary, and then figure out where to fly it afterwards. It ended up being twice the size of any helicopter that had come before, and in fact, as big as all of the previous helicopters combined. It was 49 meters across, but weighed only 54 kilograms.
So this thing is absolutely massive. Building it this big was definitely a risk. It meant that it would be unpredictable and extremely flexible. But it was also an opportunity and really forced us to come up with many different solutions at every turn. So one of the very interesting structures here on the bottom is the truss structure. As you can see, it has a whole mass of external wire bracing. It's a spider web of really, really thin lines. And this turns this truss structure into a highly efficient arch, makes it extremely lightweight. On the top, you can see the rotor, and it looks much more like an optimized wind turbine blade than a traditional rotor blade. This is something that we developed using shape optimization and computational optimization. Effectively, the computer is navigating this complex design space to come up with a solution that minimizes weight while maximizing aerodynamic efficiency. The drive system is also very interesting. Effectively, what you have at the rotors is that you have a spool of line wrapped around the rotor. And when you pull on that spool, the rotor is going to spin. And that line is connected to the pedals. So when you're turning the pedals, the rotor is spinning, just with this long line. We have about 90 seconds of line. So when your line runs out, you better be on the ground or your helicopter is coming down pretty quickly. But as long as you live about 1 minute and 30 seconds from work, I think this is an excellent commuter vehicle. control systems is another very unique solution, and this is something that we really couldn't have envisioned until we actually built it, tested it, and saw how this helicopter behaved in the air. Originally, the control system involved complex levers and a huge array of lines going out throughout the system and twisting rotor blades, but the flexibility of the aircraft just made this untenable. Effectively, when you actuated the control system, the helicopter did almost exactly the opposite of what you wanted it to do. So we ended up tearing that system apart, and we replaced it with 4 tiny lines weighing a total of 100 grams. And these lines connect the bicycle at the center to the bottom of all the rotors. And what happens is that when the pilot leans, you're actually bending this entire structure. The whole structure flexes, it tilts the rotors in the direction you want to go, and that pulls you in the direction that you've leaned. And this is something, we shed 10% of the weight off the aircraft, definitely something we could not have pictured or envisioned before seeing how flexible this huge structure was. So we built Atlas with a very small team in a small barn north of Toronto in about 3 months. It was a very fast build cycle. But flight testing was much more difficult. This is pictures of us making very small adjustments to the pitch of the rotor blades on the order of 0.02 millimeters to try to get everything in balance, making hundreds of tiny adjustments to the tension and the length of all these bracing lines. And then at the end of the day, we do some tests, we learn a little bit, and then we have to disassemble the whole thing and pack it up into a 52-foot trailer. And that's on a good day. On a bad day, we break things. We break a lot of things. This project definitely taught us and really made us understand that how much failure is a necessary part of success. There was twice that we were literally inches away from the prize when the entire thing came crashing down. Yeah. But every time we picked up the pieces, we kept on going for 2 main reasons. I mean, at that point, we knew we were close. We were inches away. We knew that it was possible. But more than that, the team was absolutely passionate and dedicated about the project goal. Everyone had come on board without the promise of pay. Everyone just wanted to see it work. So on June 13th, once again, we climbed on board to challenge the Sikorsky Prize. Thank you. So what's next? More recently, Cameron and I have been focusing on high-speed bicycles. Basically, these are recumbent bicycles inside an aerodynamic shell that are capable of highway speeds. It's very exciting for us because this is definitely a little bit more practical, a much more transferable technology. But even here, people are so quick to set limits. In 1992, the Cheetah achieved 109 kilometers an hour. And they were quoted as saying, "The envelope for speed for mankind has been closed. We have reached the limit." This was a team of elite engineers and a professional athlete, and they believed, given their credentials, that it was simply not possible to go any faster. Of course, history is full of these wonderful quotes, and you can imagine, where this story is going to go. A few years later, a Canadian cyclist and a Bulgarian sculptor came on scene, and within just a few years, they pushed the record from 109 to 132 kilometers an hour. That doesn't seem like a massive leap, but for the fellow geeks out there, the power goes with the cube of velocity, and that represents a nearly 100% increase in efficiency over what was the preconceived limit. And that's a big deal. So now every year, people gather from all over the world in Battle Mountain, Nevada, to push this limit even further. And this is a really amazing community of people that are, it's competitive, but at the same time, people are open. They're willing to share because everyone is passionate for this common goal, to push this technology further.
So what does society have to gain from people going on bikes really, really fast? Well, as Todd says, this technology is transferable and very applicable in our everyday world. Already, these bikes have an efficiency 60 times better than the average car. And this really shows that if you prioritize energy consumption and aerodynamics, that you can really do incredible things. Furthermore, like all technologies, this one is really only getting better. This is a plot of the 1 hour the 1 hour distance record for humans over the past century. And the blue line is for a standard bicycle, and it's pretty much stagnant, not going anywhere. But the green line is for these unconstrained speed machines, and it's really not showing any sign of slowing down. So this is our next challenge. We want to break the human-powered land speed record. We've already built and raced this bike, which in September went 125 kilometers per hour. We think that we can go faster. Next year, we're going to apply some more advanced aerodynamic design, look for ultra-low rolling resistance tires, and integrate some neat technologies like camera steering. Maybe eventually we'll have bikes that steer themselves. So we've measured the inspirational impact of these projects, and we know that we're having an important part of inspiring the next generation. But we really need to figure out now our next challenge, which is how we sustain this indefinitely. The great thing for young entrepreneurs these days, there are lots of fundraising methods like crowdsourcing, corporate and university sponsorship and support, YouTube advertising revenue, and we know that this is difficult, but we can sustain this and we can go on. So in the future, when we're taking on these projects, there's a lot more exciting stuff to do. We'd like to cross the US coast to coast, about 5,000 kilometers, in just 4 days on one of these bikes. There are also 2 more human-powered aircraft to make. One, to fly a marathon, 42 kilometers in just 1 hour, and another to design, build, and demonstrate a human-powered aircraft suitable for sporting competitions. Our primary goal through all of this is to inspire people to take on the great challenges and to show that through small changes in mindset and different ways of thinking, we can make massive leaps forward. And what was impossible will be possible. Thanks very much for your time.